Mass shootings are not common, but they do happen. In the past few years, we've seen attacks in Paris, Munich, Orlando, on the beach in Tunisia, and certainly in the United States. When an event like this happens, the pro-gun community will respond with a statement like, "The only thing that can stop a bad guy with a gun is a good guy with a gun." Let's look at that. In 1996, the United States Congress passed a law preventing one of their main research funding bodies, the Centers for Disease Control and Prevention, from putting money towards research that could potentially be used for gun control. And although it wasn't an outright ban on gun research, it did dampen the field for the last 20 years. And one of the few researchers who has been active, Dr. Garen Wintermute at the University of California, famously put in over $1 million of his own money so that he could continue his work in this area. Now, having said that, over the years there have been some attempts at looking into this area. And here we have a paper that does just this. It's called Dependence of the Firearm-Related Homicide Rate on Gun Availability. And it is available in a publication called PLOS ONE. Now the details don't really matter, but essentially that means that anybody can read it. It's not hidden behind any sort of paywall. And what they did was they built a mathematical analysis, essentially a set of equations that could be used to look into this question that we mentioned earlier, where we have one gunman and a mass of potential victims. Is it better overall for some of those victims, or even all of those victims, potential victims, to be armed themselves? Or will that make matters worse? So you've got these two sides. So on one side, you've got a crazed killer who will eventually run out of bullets or eventually be taken down by the police. And in the other extreme, you've got a crazed killer plus a crowd of people who are all armed. So if that armed crowd all starts shooting, will the gunman be taken down with fewer casualties than the first situation? And they look at this and they take two extremes and they say that the first extreme is where no one's got a gun and therefore there are no gun related injuries. And the other extreme is where everyone has got a gun, and they assume that when everyone's got a gun, the crazed killer won't even bother. So they assume that when everybody's got a gun, there won't be any deaths as well. And then they look at what could happen in between these two. And they say very clearly that what they're trying to do is inform the debate around this and generate discussion. And one of the things that they're trying to do with their formulas is identify in their formulas where data is missing. So what bits of their formula do we need additional research on in order to inform this debate? Now there is, by one of my heroes, James Fowler, a write-up on this paper in Nature magazine, which is the place to go to if you want to look at this a bit further, because this is written for the general reader, whereas this is heavy on the mathematics. Unfortunately, however, this is hidden behind a paywall, so you won't be able to get this for free, whereas you will be able to get this one for free. But if you don't want to wade through this dense mathematics, what else could you potentially do? Well, one thing that you might want to do is look at an agent-based model. So in this paper, it says that they envisage the situation following a discrete time Markov process. And that's a fancy way of saying we've got a series of time steps, and whatever happens in a particular time step is dependent on what happened in the time step before it, and so on and so forth back down to the first time period. So the situation essentially can evolve over time, and that is exactly the same sort of thing that happens in an agent-based model. So how could we construct an agent-based model that might examine this problem? Okay. Okay, so here we have an agent-based model, and this model is all about people leaving a building, running from a building. And there are a number of these available online, so I've picked one that comes from the Net Logo project prototype. And it's well written up here. I'll put the links down at the bottom somewhere, you can check those out later. And what we have is a series of dots, and each dot represents a person. And when we click run, the agents will panic and try to leave the building. So here they are running for the doors, and this is a model that has been built up, and there are various models online varying in their sophistication. This is quite a simple one, and after a few seconds everybody has left the building. And we can use this as a starting point to construct an agent-based model to look at this. And that's exactly what I've done here. So all I've done is take exactly that same model, and I've added in a person, an agent, that all the others try to escape from. So there it is down there, the blue circle. And this time when I click go, what will happen is the agents will first of all try to put some space between themselves and the blue circle, who's going to be our gunman eventually. And then after they've got some space, they run for the nearest exit. So all we need to do next is fit in the shooting behaviour now. So if we go back to the +1 paper, what the authors did was they set up a series of equations and discussed them, and then they decided to go ahead and populate those equations with real numbers. And those numbers came from anywhere in the literature that they could find values. And in some cases they had to make their best guesses, but the point of the paper was not really to inform policy, but it was to stimulate a debate. And we can do the same thing here. So here, with my agent-based model, to give our shooter some realistic accuracy in their ability to shoot, we can look around to see what other studies have been done. And we've got this one here that has been published in Police Science and Management, called The Real Risks During Deadly Police Shootouts, Accuracy of the Naive Shooter. And that gives us some indications of how a novice shooter and an expert shooter might be able to act with a handgun at different distances. And we can build all of that into this model. So the way this works is, let's say for example that we wanted to give our agent 30% accuracy. What we would do is, inside the computer we would program essentially a coin, and we would toss the coin, and 30% of the time it would come up heads, and 70% of the time it would come up tails. And every time our shooter wants to fire a bullet, the computer tosses the coin, and if it comes up heads, his shooting is accurate, and if it comes up tails, it isn't. Now, if it isn't accurate, it doesn't mean that he's going to miss completely, because there could be someone standing beside the person that he was shooting at that he might hit. And we are talking here about injuries rather than deaths. We're not going to build into this model deaths. So let's have a look at how everybody reacts now. So if we just slow it down an inch and go. So people are running from the shooter, they're running for the doors, and down here at the bottom we can see a count of how many successful hits the shooter makes. And then all we have to do is add in some good guys with guns. So we can add in as many as we want, but let's add in just one to begin with. And there they are. So we've got a yellow person who will be prepared to stand their ground and shoot. And we've got our one shooter, and then we've got all the innocent people. And this time we can do a couple of counts. We can count the number of times that the shooter hits someone, and we can count the number of times that the yellow hero shoots someone. And we can do that thousands of times over, with varying degrees of accuracy and varying sizes of the people who are in this space. And I did that earlier. So what results did we get? Well, first of all, if we go back to the +1 paper, their results suggested that a ban of private firearm possession, or possibly a partial reduction in gun availability, might lower the rate of firearm-induced homicides. Now our situation is slightly different. We've got an enclosed space, we've got one shooter, and we are varying the number of heroes. But again, broadly our results support this. Certainly if a lot of people have guns, it tends to turn into a bloodbath. So the best case scenario there was obviously when the heroes were experts, and in the number of runs that we did this 100 times, and an average of 32 people were injured when 50 people had guns, and when nobody had a gun in the same situation, 29 people were injured. So it's not a huge difference, and in that situation it was best when there were 3 heroes. If there are 1 or 2 gunmen who are prepared to stand their ground, sometimes they make a difference and sometimes they don't, but they don't make it much worse. So there you have it. There is one potential way of studying something where it is difficult to find data. We could do a mathematical analysis with equations, or we could set up an agent-based model, and we can analyse them both in very similar ways, by experimenting with parameters, by experimenting with values for accuracy, and with values of how many exits there are, or how many people are in the space, or how many heroes there are.